All right, let me go ahead and get started. I'm going to let the my pencil warm up a bit before start recording. This is just a reminder that this is the last week before the first midterm. The first midterm will cover material that you have seen in homework 0, 1, 2, and 3. That means that there is some material that we've talked about in class that you will not see on the midterm. In particular, the material from today's lecture will not show up on the midterm. Other things like there was a question on Piazza about Hahn and Wood's algorithm. We saw it in class. There was a wave at it at the labs, but there was nothing on the homework, and therefore it's not in scope for the exam. On the other hand, homework 0 is meant to test prerequisites. So in principle, the homework covers everything that you have seen since you were born up until last Thursday, with a particular emphasis on the material in this class. That means, things like induction, we assume that you can do, and that will be in scope. Well, let me go through the list of announcements on the web page before I talk about other things. The exam will be split across 2 rooms. Most of you will be in here. About a third of you will be in Siebel. Which room you go to? We've got almost exactly 300 students, and this room will hold under exam conditions almost exactly 200, and the room over in Siebel will hold under exam conditions almost exactly 100. So please do pay attention to this. If your discussion section starts at 9, 10, or 11, congratulations, you go to Siebel. If your discussion section starts at noon or later, congratulations, you'll be taking the exam in here. The second midterm, we are all in Lincoln Theater. That was the room we got. There's a conflict exam, which I've already talked about a little bit. There's a registration form. Please fill that out by the end of the week. We will do our absolute best to make sure that everyone who needs to take the conflict exam for reasons outlined in the student code can take the conflict exam. So here's what the form looks like if you haven't already seen it. It's just listing, why you might want to take it. Who are you? We want your real name, not your grade scope name. Why and when. And so this is just a bunch of 2-hour blocks. For purposes of scheduling the conflict exam, I am assuming that you will be free on Tuesday from 11 to 12:15, because supposedly you're supposed to be in here, and I am explicitly excusing you from attending lecture on Tuesday. Now, you may have a class before or a class after, which is why we're asking about these 2-hour blocks. Let's see. There's a bunch of study materials. So in particular, there are 3 past exams. The first 2, Fall 14 and Fall 16, are from the last 2 iterations where I wrote the exam, or most of it. Spring 17, this is a more recent exam from, actually I'm not sure whether that's Spring 17 or Fall 17 now that I think about it. This is the exam that Sariel gave, which is similar to Instructor to the exams that I've offered. I wasn't able to find on the web exams from Mahesh or Chandra, so I assume they don't want their exams distributed. In addition to those previous midterms, which may differ slightly from what we're doing now, so in particular, if you look at the Fall 16 exam, there is a bad question. you know, you might want to understand what's going on as a way of studying for, you know, the Contextfree grammar material, but we are not going to ask a question like this because it takes half an hour to write down the solution, even if you know exactly what you're doing. Stupid mistake. We will do our best not to do that. There's also this extremely large question. You'll notice that there's 16 pages, and, well, it's a lot. Now, the first time we released this particular trove of questions, the last time I taught 374, we got a complaint from a couple of the students saying, there are way too many questions here for us to understand them all. I want to suggest that those students were missing the point. There are basically 8 or 9 things: induction, regular expressions, DFAs, NFAs, epsilon transitions, product constructions, fooling sets, language transformations, and context-free grammars. That's 9. There are 9 things, right, which are of varying difficulty in understanding and varying difficulty of actually being able to execute. The point of this trove of questions is to say, for you to say, I wonder how comfortable I am with fooling sets. Let me look at the dozen or so fooling set problems, pick 2 or 3 out. And if I look at the 2 or 3 that I pick out, and yeah, I can do one of these questions in 20, 30 minutes, then great, you're prepared, because that's what we're going to be asking you to do on the exam. If not, this gives you an opportunity to say, what is it about fooling sets that I don't understand? Is it something about coming up with the fooling sets? Is it do I understand the boilerplate? Do I find myself defining a fooling set, but then picking out X and Y that aren't really arbitrary, but have some additional special structure, like the length of X is always 1 less than the length of Y, which can't happen, and then asking for help on those points from the other students in the class, on Piazza, in labs, in office hours. Okay, so this is meant for you to test your mastery of the material, the ability to actually do the work, and check where you have weaknesses so that you can address those weaknesses walking into the exam. I want to make, there's one sentence written here in red that I want this to be very, very clear about here. Understanding is a trap. If you look at the questions and go, yeah, I know how to do that. If you read the lecture notes and you say, sure, I get it. If you read through the old homework solutions and you say, okay, I understood how this works, you're being led down the garden path. This is a trap. This is a distraction. What you should be asking is, can I do this? And if you can, cool, you'll do great on the exam. If all you have is, I remember how homework 1 worked, you're not going to do as well on the exam. So this is the point of this. This is the point of the discussion we're going to have in labs on Wednesday and Friday. This is the point of having the review session on Thursday. Another aspect of this is, if you look here at the exam policies, everyone can bring in a sheet of paper or 2 one-sided sheets of paper if you insist, with whatever you want that you wrote on it yourself with your hands. The reason why, I used to allow cheat sheets with just arbitrary whatever, but I discovered the last time that we did 374 that a disturbingly large fraction of the students were just taking the old homework and lab solutions or taking the lecture notes and photocopying them down so they fit on 1 page. And I am not exaggerating when I say this. The most extreme example of this is somebody managed to photocopy a 6x6 grid of pages on each of 4 sides for the final exam cheat sheet. It's 144 pages of utterly illegible notes and solutions. Other people would take, like, so I would encourage you, start a Google Doc, start 3 Google Docs to crowdsource solutions for these things. Other people would just bring photo-reduced copies of that Google Doc, thinking that if I know the solutions to these questions, then I know the solutions to the questions that are going to be asked. And this is, the data suggest, this is a really ineffective way of studying. The point of having the cheat sheet is so that you are forced to distill what is important, what you need to remember, what things you need to remind yourself to get the skills into your hands to do well on these kinds of problems. Because the problems you're going to see on the exams are not going to come from that incredibly long list. Because we could make that twice as long if we wanted to, or 3 times as long if we wanted to. If for some reason writing the cheat sheet out by hand is actually a problem in terms of things like, this would be one of the things that you might ask for address accommodation for if you have dysgraphia or dyslexia, come talk to me. But even those of you who are used to doing things on iPads or used to typing things, great. Block out the cheat sheet on the iPad, block out the cheat sheet in typing, and then copy it by hand onto a piece of paper. And the act of writing it by hand, which is the same act, the physical act that you're doing when you're taking the exam, the point of that actually is not to get it onto the piece of paper. The point of that is to get it into your hand. So often what students report is when they've built these cheat sheets, they walk into the exam, they pull out the cheat sheet, and then they never look at it because they don't need to. They just remember, they glance at the cheat sheet, oh, right, I remember writing that, and they keep going. Okay. That's where we want the boilerplate to be. Not in your brain, but in your hands. Muscle memory. And so you can focus on the bits of creativity you need to solve the problems. Okay. We will ask you to submit your cheat sheets after the exam. So if you want a copy of your cheat sheet for later, make that copy before you take the exam. We're not planning to hand the paper back to you. Everything is going to be scanned and uploaded to Gradescope for grading purposes. So once the cheat sheets come to us, it's going to be difficult to get that massive pile of paper and get the cheat sheets back out and back to you. So please record the cheat sheet yourself before you walk into the exam if you think you're going to want to keep it. Question? That's why you should make a copy of it. No. Yes, I'm insisting that you write it again. Right? The point is to get it fresh in your mind. Right? If you just say, oh, all right, I did that back in February, in May, and you take the piece of paper and you put it down, and you look at it and go, oh, crap, I did this 3 months ago. When was the last time you looked at code that you wrote 3 months ago? Do you remember everything that went into it? But the code that you wrote a week ago, you probably have a good chance of remembering what your intuition, what your intentions were. Yeah, question over here. Oh, I'm sorry. I will fix that. I probably, yeah. You can, if you can find your way to Sariel's webpage. So I think, in fact, it should be fall 2017. You can find the midterm here. Yeah. We will not provide solutions to the practice problems. We will not provide solutions to the old exams. We've given you many, many solutions already for homeworks, for labs, for practice problems on the homework, for like 3 times as many problems in the labs as you've actually solved. At this point, we think you know what a correct solution should look like. But feel free to say, I solved problem B17 and think this is right on Piazza, post that and ask for feedback. And other students and the course staff can chime in and say, actually, you missed a base case here. The idea is right, but you need to, that kind of feedback. Again, this is inoculation against thinking that knowing the solutions is the point. Knowing the solutions is not the point of the practice problems. Knowing the process is the point. And the only way to really understand, to master the process is by doing it, not by passively observing it. This is also, actually, by the way, I think I said this at the beginning of the semester, this has been the whole point of having the labs and having the homeworks, is to give you the opportunity to practice the techniques, to get the techniques into your fingertips, not to show you, here's a problem and now here's a solution. Okay. Are there any other questions, administrative questions about, oh yes, one more point about the exam. We will be scanning these things and uploading them to Gradescope for grading. For privacy reasons, that means the front page of the exam booklet will ask for your real name, your net ID, your Gradescope name, and your Gradescope email address. If the last two are the same as the first two, just say same, right? But then every other page of the exam, we're going to ask you, as a redundancy thing, to write your Gradescope name on the top, so that we won't upload the cover page to Gradescope, we'll upload everything else. Because if you have reasons not to use your real name, we need to respect that. So, but we also need to be consistent about being able to identify whose exams are what, and all the stuff on Gradescope, we only know your Gradescope identities. So please be careful about this when you're filling out the exam. Okay? Other administrative questions, and if other ones come up later, please feel free to ask on Piazza, ask in class on Thursday. Great. So let me quickly get set up here for the lecture and start recording and all that other wonderful stuff. And then we will talk about Turing machines. Hope. There we go. Okay. So for the last 4 weeks, I guess, we've been talking about very elementary machines to do computation, called finite state automata. And we've been talking about very structured sets of languages, sets of strings that these automata can recognize. These are so-called regular languages. So I have, DFAs, NFAs, regular expressions, all talking about regular languages. And the one way to think about what a regular language is this is a language that can be built from individual strings by sequencing, branching, and repetition. But no function calls, no variables with unbounded scope. You can have a finite number of, if you're thinking about this as a class of algorithms, you can have a finite number of algorithms, each of which can take on a bounded number of values. And when I say bounded, I mean at compile time, you know this variable can take on at most 10 values, that variable can take on at most 5. But otherwise, no memory at all. The input comes in one symbol at a time. You have an internal state, which is one of a finite number of things. Whenever a symbol comes in, you change your state. When the input's done, you're either in a state that you like or a state that you don't, and that's as far as computation goes. Then we extended this a little bit to context-free grammars, which describe what are called context-free languages. And to our suite of tools that we can use to build the language, we added recursion. So I can say, I'm going to build up my language L by concatenating these other two languages, A and B, and A is going to be something that maybe I built by sequencing and branching and repetition, some regular language, and B is something that I'm going to get by concatenating A and L, where L is the thing that I'm defining at the top level. So the context-free grammar essentially mirrors a program that's written as a series of modules or subroutines or functions that have unrestricted ability to call each other. But otherwise, there's no memory. All the variables take on a bounded number of values that I know in advance and so forth. The ability to recurse, however, does allow me to remember an unbounded amount of stuff in the sense that I have a recursion stack. Whenever I make a recursive call, I tell the recursion fairy, go do this thing. Okay, now how do you implement the recursion fairy? You take your current scope, your current set of variables, and you stuff it onto a stack. And then you jump over to the starting instruction of your subroutine, and you say, okay, I'm going to initialize all my variables. Now I'm starting afresh. The variable that I'm calling x now isn't the variable I was calling x a few instructions ago. It's a new x in a new scope. And then I run my thing. I get to the return statement, return true or false. And then I take my old scope off the stack with the return value added in as a new variable. And so the stack allows me to temporarily store stuff and then retrieve it again in the opposite order that I stored it. But this is a very limited amount of memory, a very limited style of memory. It doesn't allow you to, for example, remember two integers. You can remember one integer by having it be encoded in the depth of the stack, but you can't remember two. And so languages that require you to remember two integers to recognize are not context-free. The most general version of this sort of language hierarchy, I'll add one more step, one more capability to either the set of languages, which somewhat confusingly, the set of languages now that I'm defining is called the recursive languages, even though we got recursion already. And then the machine model is this more general thing that I'll describe in a minute called the Turing machine. And what you're adding to your suite of tools is unbounded memory. Okay? So you not only have the ability to recurse, make function calls, but you have variables that can store an unbounded an unbounded number of different possible values. So this would allow you, for example, to have a spare variable lying around that is just a string, or a spare variable lying around that represents, a pair of integers, or a binary tree, or a Python program. Right? There's an unbounded number of syntactically correct Python programs. So a Turing machine, in principle, allows me to have a variable of type syntactically correct Python program, which I can then manipulate algorithmically. So Turing machines are named after their inventor. They're one of the very small number of things that are actually correctly named after the person who actually discovered them. Turing was a 23-year-old recent college graduate. And he wrote this paper where as a 23-year-old, he solved one of the biggest outstanding open questions in mathematics at the time. So in the International Congress of Mathematicians, and I believe it was 1901, David Hilbert gave an address where he listed 23 problems that really bugged him and really bothered the mathematical community. And one of them was called the Entscheidungsproblem, which is German for the decision problem. What Hilbert wanted was an algorithm that could take a mathematical statement and, at least in principle, if not in practice, mechanically derive a proof of its truth or its falsity. If I tell you a theorem, the Riemann hypothesis, okay, is that true or is it false? I would like to have an algorithm, a decision procedure, where I could put the theorem in at the top, turn the crank for a quintillion years, and out would pop a proof that the theorem is true or a proof that the theorem is false. And what Turing did at the ripe old age of 23 is say, nope, can't happen. Now, technically he wasn't the first to do this. You may have heard of Gödel's incompleteness theorem. Gödel was about 8 years, I think, before Turing's paper. But Gödel didn't think that Gödel solved the Entscheidungsproblem problem. Gödel didn't actually like the whole Gödel numbering stuff as describing what an effective procedure is. While Turing was writing his paper, a faculty member at Princeton named Alonzo Church invented the Lambda calculus in 1935. And again, this offered another way of proving that there are certain problems where there's no algorithmic solution. And Gödel, who was at the Institute for Advanced Study, was like, well, it's better, but that's not, I mean, this is all abstract recursion function stuff. People don't work like that. Remember, in the 1930s, when you say the word computer, you mean a person. Probably with one of those little mechanical calculators to help them, but you mean a person who computes. What Turing envisioned was, let's imagine what a human being can do if the human being has an inexhaustible supply of paper. That's ultimately what a Turing machine is. It's a computer, i.e. a human who computes, with an inexhaustible supply of paper, memory. So what do humans do when humans do mathematics? Humans manipulate symbols. Humans manipulate symbols according to certain rules. If you see an integral, there's a change of variable formula, which is an algorithm for rewriting the integral in a different form. And then there's algorithms for doing, you know, I see here's the integral of sine. Let me substitute in negative cosine. The calculus that Newton and Leibniz may or may not have invented independently was not the invention of differentiation and integration. It was the invention of a suite of algorithms that allowed people to do calculus without thinking. That's what math is when humans do it. It's pushing symbols around. So let's imagine an abstract machine that can push symbols around and has access to an arbitrary amount of paper. Now, the way Turing formalized this is by saying, let's imagine that I've got this infinite sequence of pieces of paper, which is normally referred to as a tape. And I've got a person who can focus on one piece of paper at a time. Now, of course, you and I, when we're doing this, maybe we have 5 pieces of paper on the table at a time that we're focusing on, and we're trading one. But this is kind of like a product or subset construction. You can think of one of these cells as just an abstraction of how much you can actually have in your short-term memory or in your focus of attention at a time, given what you can see. Now, the human beings, let's imagine for purposes of mathematical abstraction, this is a finite state machine. This is a machine that can exist in a finite number of states. I'm trying to add 3 plus 4. I'm trying to solve this differential equation. I need to turn the page now. Where is my coffee? This is only a small number of these, maybe in the Googles, but still a finite number. And based on what the finite state machine sees on the current piece of paper, and based on its internal state, the finite state machine changes state. So if I walk into an exam in a particular state of mind, I pick up the exam and I look at it, my state of mind has changed. But if I take as a hypothesis that I only have a finite number of different states of mind, this is like a DFA. I'm in a finite number of states, I receive an input, midterm 1. My finite state machine changes to a different state. But the finite state machine is allowed to change what is written on the paper and is then allowed to move. So, go away. So for example, if you take, a serious abstraction here, and just imagine that all I can write on a single sheet of paper is a single bit. And it turns out this is actually sufficient to describe the more general model. And inside the finite state machine, I say, okay, I'm in state 473. Okay. Then in a single step, what the Turing machine is allowed to do is 3 things. The first thing is the state machine can change the number that is written on the tape at that position. I can replace the piece of paper I'm given with a new piece of paper. I can take notes. I can erase. Can change the information that's directly in front of me in my short-term memory. I can change my internal state. And I can move to the previous or the next piece of paper. So imagine here's the piece of paper that I'm looking at directly in front of me. I have an inexhaustible supply of paper to my left and to my right. I can take this piece of paper, put it on the stack on the right, take the piece of paper on the left, and look at it again. Now, this is a very, very constrained model. But as I'm hoping to be able to convince you, it actually does capture, not in terms of efficiency, it's very, very slow, it's very, very inefficient, but it actually does capture everything that you think a computer does, provided that you ignore things like I/O and networks and parallel, but if you think of a computer as a device that takes in data, thinks for a while, and spits out data, this completely captures what you imagine computers can do. Okay. On the other hand, there's something else about Turing machines that the other machine models don't have. And this was something that the way Turing proved the Einstein's problem can't be solved, is a finite state machine is, a Turing machine is ultimately a finite state machine. I have a set of states, I have an input alphabet, and I have a transition function. The transition function takes as input what is my internal state and what am I looking at on the tape, and has in the output what is my new state, what do I write on the tape, and do I move left or right? Yes, question? The current state is only one of the finite number of positions of the gears inside this box. Where you are on the tape is invisible to the machine, unless you write on the tape where you are on the tape, which you can do. You can imagine, when the finite state machine reaches over here where it's blank, it can say, okay, I'm going to use the next block of cells on the tape to write down the next address, which I'll copy from over here and increment over there, and then I'll initialize it with some zeros, and then I'll back up, and from now on I'll pretend it was that way all along. Right? This is the sort of thing one can do with the Turing machine. So by definition, the address of the machine, where it's sitting, is not known to the machine, but one can build machines that carry that information along on the tape as it's needed. Okay. So a Turing machine is a finite state machine. It has a transition function that takes as input, what's my state, what do I see, and has as its output, what's my new state, what do I write down, and how do I move. In other words, a Turing machine can be described by a big table. And that table can be described by a sequence of bits, a string. And that string can be fed to a Turing machine as input. And moreover, because the semantics of that string are so simple, because it's just a finite state machine, you can actually build a Turing machine that takes in that string and interprets it as a Turing machine. So this is very much along the same lines of, I have a JavaScript program that will read in the source code for a Python program and execute that Python program. Except the JavaScript program is also written in Python. Okay. What language are most C++ compilers written in? C++. That's weird. Right? So it's exactly the same idea that on the one hand, it's descriptive of arbitrary, I do need to put this in quotes, computation. Everything that you can imagine a human or a digital device actually doing. And on the other hand, it's simple enough that it's fairly easy to convince yourself that it can simulate itself, right? That I can take a Turing machine and encode it as a sequence of bits and feed that to a different Turing machine which actually understands what those bits mean. Now, being a little bit dangerous here by anthropomorphizing things. It's not that the machine actually understands, it's just following its own set of states and transitions. And then Turing said, okay, let's take a machine, let's call this M, and it's going to take as input the encoding of some other machine M prime, and it's going to output true or false whether M prime halts. Yeah, I don't know, 0 or 1, accept or reject, however you want to say it. So let's assume this machine M exists, that I can take in a description of a Turing machine. I can go into more detail what the description of the Turing machine looks like, but if you want, imagine this is a piece of Python source code. And it analyzes this machine and says, if I just start the machine on a blank tape, does it ever halt? Or do I ever run off to infinity? So one thing I have to point out here is the word halt. It's different from a finite state machine. In a standard DFA, when you have consumed the input, you halt. You can think of a DFA as a Turing machine that can only move its head to the right, which means what you write down just vanishes. You'll never get back to it again. But for a Turing machine, I have to go either left or right. And so it's not a priori clear that there's a natural place for the machine to say, okay, I'm done. So one of the states of the machine is halt. In fact, the way I have it formalized in the notes, there are two halting states. One of them called accept and the other one called reject. And the Turing machine accepts its input if it ends up at any point in the execution in the accepting state. and the Turing machine rejects its input if it ends up at any point in the execution in its rejection state. And the third option is it infinite loops. So it's easy enough to write a Turing machine that says, if I'm in, I'm going to have a Turing machine that has two states, one called left and one called right. If I'm in state right, then no matter what I read, I leave it alone and I move to state left and I move the machine to the right. If I'm in state left, then no matter what I read, I leave it alone, I move the machine to the left and switch back to state right. And then the machine's just going to go, you know, forever and ever and ever, and it'll never enter the accept state, it'll never enter the reject state, it will never halt. It will never return a value. So the question here is, given a description of a machine, does it have an infinite loop like that? Or can I prove somehow by mechanically analyzing the machine that eventually it will either accept or reject? And well, let's suppose such a machine exists. And then what Turing did was the following. I'm actually going to feed in a description of M itself into the machine. See, I'm waving my hands a little bit here. Maybe I should say, just to keep this simpler, this asks whether M prime accepts. Now, you might think, oh, I just run M prime, and if it accepts, I return true, and if it doesn't, I return false. But M prime might infinite loop. And so I can't ever definitively say no with the naive thing. Given this fanciful Turing machine M that decides whether another Turing machine ever ends in an accept state, I'm going to do the following thing. I'm going to feed its own description in as input. And then if I return true, I reject. And if I return false, I accept. Okay, so I've just defined a slightly larger machine. If there were a Turing machine that could solve the halting problem, could always decide whether another Turing machine accepts its input, then I could feed that machine to itself and negate the output. And if I had set this up correctly, which I don't think I quite did, you would end up with a contradiction that this new machine returns accept if and only if it returns reject. Right? If you can always answer the question, will this machine halt, then think of the following algorithm. I'm going to call this algorithm Turing. If Turing says yes, said no, say no. If Turing says no, say yes. Right? There's no consistent answer to whether Turing says yes or no. This is me saying, I'm lying to you. Right? The old, all cretins are liars paradox. But this is something that, because the Turing machine can simulate itself, you can actually do this experiment. You can actually write a piece of Python code with the property that if you had a library subroutine that says Python code halts, you could write a piece of Python code that halts if and only if it doesn't. And so now I have a theorem, this Turing machine halts, which cannot be proved mechanically. And so you cannot mechanize mathematics. Hilbert's dream of a decision procedure for arbitrary mathematical theorems, sorry, doesn't exist. Life is more interesting. Things are weird. This was arguably the birth of computer science as a scientific discipline. This was, wait a minute, you mean that stuff that we've been doing for thousands of years? We've been computing for thousands of years. We've been doing calculations for as long as we have been human. But suddenly the question, can we compute everything? The answer is no. You can't do everything. Then becomes, what can we do? What can we do quickly? What can we do now? Why hasn't Amazon delivered my water bottle yet. Right. Why hasn't season 3 of The Magicians just all come out so I can binge watch it? But this is where this started. So let me give you a concrete example of what a Turing machine actually looks like here. Right, so this is a description of a particular Turing machine. I've given the description in 2 different forms. I don't want to necessarily walk through the precise details here, but this particular Turing machine recognizes is this language, 0 to the n, 1 to the n, 0 to the n. This is not a regular language. Hopefully you can see the fooling set proof almost immediately. This is also not a context-free language. That should be less obvious, but at least intuitively, it's hard to imagine an algorithm that recognizes strings in this language that doesn't count at least 2 things. Count the first zeros and the last zeros, or count the first zeros and the middle ones. So it's not a context-free language, but you can write an algorithm to decide whether a string has this form, and this is just a very, very simple form of this algorithm. Now, formally, the pieces of the Turing machine look like the following. So a Turing machine is a tuple that has a bunch of pieces. Sorry, I need to put in U first. Okay. So gamma is what I'll call the tape alphabet. These are the symbols that I'm allowed to write down. Okay. In this particular case, the tape alphabet consists of the digit 0, the digit 1, the letter X, a $, and a special symbol called a blank. And there's a special symbol, which I represent here by a square, called a blank. And the semantics here of the blank are all but a finite number of cells in the tape have a blank on them. This represents an empty piece of paper. The tape alphabet allows you to write a blank onto the piece of paper, meaning, okay, I've got a bunch of stuff on this paper, just erase it all, start over. But I assume initially my unbounded length tape, all the cells are blank, except possibly for the input, which will be written as part of the tape alphabet. Okay, so I also have an input alphabet, which is a subset of the tape alphabet, but without the blank. So in this particular example, the input alphabet is 0, 1. So what I'm given as part of my input is a binary string written onto the tape, and the rest of the tape is filled with blanks. And the other symbols in the tape alphabet, in this case the X and the $, these are things that the extra symbols that the machine is allowed to use to record memory on the tape. There's a finite set of states, and there are 3 special states: start, reject, and accept, that belong to this, this set. These are 3 distinct states. Start is, as the name suggests, the state that the machine starts in. If at any point in the future the machine finds itself in the accept state, the machine halts and says, yes, I accept this input. If the machine ever reaches the reject state, it immediately halts and says, no, I reject this input. The machine might never reach either of these 2 states, in which case it enters some sort of weird infinite loop and you never hear from it again. this is kind of an unavoidable feature of the model. And then I have this transition function delta. It takes a state, but that state can't be accept or reject, because when I accept or reject, I already know what's going to happen. I know I'm immediately going to halt. And it takes in a symbol in the tape alphabet, and it returns a new state, which might be accept or reject. And it returns a new symbol to write onto the tape, and it returns an instruction to move the head either left or right, which I'm encoding here as -1 or +1. So this particular Turing machine here has 1, 2, 3, 4, 5 states that are not accept or reject. So there's a total of 7 states. The states are named start, seek 1, seek 0, reset, and verify. And I've deliberately written this in a style that hopefully, if you actually sit down and play with it, reveal what the purposes of these states are. So for example, if I'm in state seek 0, what I'm doing is I'm moving the Turing machine head, the thing that looks at the tape, to the right, trying to find a 0. If I'm in seek 1, I'm moving to the right, trying to find a 0. When I find a 1, when I find a 0 in state scan seek 0, I will mark it with an X, start moving to the left, and enter the state reset. So how does this machine evolve? All right, any questions about definitions? All right, how does this machine evolve? Okay, so here's the transition table again on the left. Here in the middle, I have a sequence of what are called configurations. The configuration of the Turing machine has 2 parts. The first part is, what state am I in? And the second part is actually 2 parts. What state am I in? Where am I on the tape? That's what this black arrow represents. And what's currently written on the tape? Now, I want to distinguish here between states and configurations. A Turing machine can live in one of a finite number of states, which I know in advance. This Turing machine has 7 states. But because the configuration includes the contents of this unbounded tape, there are an infinite number of possible configurations that I could be in. Both because there are an infinite number of strings that I can write onto the tape, and because there are an infinite number of positions that the controlling head can be in. So let's start here at the beginning. So if I'm given the string 0, 0, 1, 1, 0, 0 at the top middle there, I'm looking at a 0 and I'm in state start. And so I'm here. I'm going to replace that 0 with a $sign. I'm going to change my state to seek 1, and I'm going to move to the right. Okay. Now, in step 2, I'm in state seek 1, looking at a 0, so I'm here. I didn't find a 1, so I'm going to leave the 0 on the tape and continue moving to the right. And now, at this point, watching me go through this step by step is like watching paint dry. Right? We're not going to do, I don't know, hopefully you never had to do this in your architecture classes or your machine programming classes, watching somebody walk through machine code. That's what this is. This is machine code for the most ridiculously simple machine you can imagine. 7 states, a 4-state tape alphabet, 5 symbol tape alphabet, just returns yes or no. At a very high level, what's going on is in this first part of the first run of the algorithm, what I'm doing is I'm looking for the first 0, the first 1, and then the first 0 in their corresponding runs. I'm going to mark the first 0 with a $sign, the first 1 with an X, and the first 0 in the second run with an X. Then I back up. I hit the $sign. That tells me I'm at the beginning of the string. This is the part where I've already processed. So move forward, find the next 0, the next 1, and the next 0. And again, mark them with $X and X. Then I go back and I find myself looking at a $sign. And if the symbol after the $sign is an X, that means I've $'d all of the initial zeros. And I need to check whether I've put X's on all of the remaining 1s and the remaining zeros. So I scan in this set verify. In the state verify, I scan to the right. If I see an X, I write a $sign and move to the right. If I see an X, I see a $sign and move to the right. If I ever see a 0 or a 1 in this state, I reject. But if I manage to get all the way over here to the blank, then I accept. Okay. So on the right, you can also see an example of what happens for a string that's not in this language. There's not enough 1s. And so what happens in this case is when I get to either a seek step where I'm looking for a 1 or the verify step where I'm looking for all X's, I see a symbol that shouldn't be there. And at that point, I just reject. There's this lovely graphical way of describing what's going on. It is a finite state machine, after all, so I can write it down as a finite state machine. But now the arrows have this much more complicated thing written on them that if I'm in state start and I see an X, I should write a $sign and move to the right and go to state verify. We're not going to be designing these things. So I'm just showing you this to convince you that there are somewhat interesting things that you can do with this. Okay. Now, this is a very, very limited vocabulary of things that you can do. And you might notice a few things that you would like to be able to do with computers that you can't do with Turing machines, or apparently can't do with Turing machines. One of them somebody already pointed out. The definition of Turing machine doesn't allow you to know where you are on the tape. But as I hope I at least wave my hands a little to convince you, you can actually just write that information onto the tape as you get to new parts of the tape. So what other things would you like your computer to be able to do that Turing machines don't show you a way to do? Good. This is a big one. Okay. We normally think of computers as having an unbounded address space, but if I want something in the 374th address, I just say *374, go, or A of 374. I have this indirect access to memory. Now, I can simulate random access memory by storing tuples of the form address value on the tape, where address is a sequence of bits and comma and value is a sequence of bits. The brackets and the comma are symbols in the tape alphabet. Now I want to look up what the value in a particular address is. I write down onto the tape what my current state is, so that when and the marker that says I want to come back here. Then I scan forward until I see an address that matches the one I'm looking for, and then I copy the value down. Now, this seems like a little bit weird, because how do I even remember what address I'm looking for? And so building up to this, as a prerequisite, I want to be able to handle multiple tapes. So I have maybe several different sequences of symbols, each with their own tape alphabets. And I have my finite state machine sitting here, but it can read different parts of each tape. And now my transition function, when it doesn't depend on one state and one input symbol, but in this case would depend on one state and three input symbols. And the output of my, my transition function would be, what's my new state? What do I write on tape 1? What do I write on tape 2? What do I write on tape 3? Do I move tape 1 left or right? Do I move tape 2 left or right? Do I move tape 3 left or right? It turns out that you can simulate a 3-tape Turing machine with a 1-tape Turing machine. There's a transformation that mechanically takes a 3-tape Turing machine, and just like the mechanical transformations you've been doing with DFAs, like reverse the language or complement the bits or stutter the characters, there's a similar kind of mechanical transformation that can take a 3-tape Turing machine and turn it into a 1-tape Turing machine. And then you can declare one of those tapes to be your memory, and one of them to, say, be like a register, say an address register, and one of them to be like a data register. And now on the first tape, I have these address value pairs written down. And as I scan to the right with tape 1, in the middle, I'm just scanning back and forth. So I compare the addresses symbol by symbol, and then I reset. And I compare the addresses symbol by symbol, and I reset. Compare the addresses symbol by symbol, and then I reset. When I find the address that I want, I copy the value from the memory tape onto the data register tape, and then reset the normal execution. Maybe that's actually even a 4th tape that this is like, I don't know, local variables or something. And maybe even I have a separate tape to represent the input. Having 5 tapes, having 7 tapes, having 42,729 tapes can all be simulated with only having 1 tape. But once you have these different kinds of tapes, then you can simulate slowly random access memory. There's another thing that you would like maybe your machines to be able to do besides random access memory. Actually referred to this a little bit already, but yeah. Okay, so doing things in parallel. This is more a question about how to do things quickly than it is doing things at all. So the Turing machine model is absolutely terrible for doing things quickly. It's not designed to show I can do this fast. And so you can imagine sort of arbitrary levels of parallelism models of computation where I can't do that with a Turing machine because I need to be able to write down how many tapes there are. And in a single step manipulate that many tapes. But anything that one can do on a parallel computer, one can do on a serial computer, just slower. So the same is true here. What other kinds? There's one other kind of thing that you use when you design algorithms or when you write code. Yeah. Subroutines. And in particular, recursion. Remember, at the very beginning of the lecture, I said I'm adding memory to things you can do with context-free grammars. And the thing that distinguishes context-free languages from regular languages is how do you do recursion or function calls? Because once you have one, you have the other. Well, this is actually not so hard once you get the idea of multiple tapes. You just add on another tape. That's the stack. And as you push things onto the stack, the head that's reading this red tape moves to the right, and when you pop things off, it moves to the left. Okay, so this is, in effect, when people normally think about the equivalence between recursive and iterative code. You say, oh, I never need to write anything recursive because I can always just implement the stack myself and then make it iterative. Well, Turing machines don't have recursion built in, but because they can implement stacks as another tape that you can write data on, then one can leverage that into implementing recursion iteratively. As opposed to context-free grammars where the recursion is kind of baked into the model. There are machine models that kind of deal with context-free grammars, but they either also have recursion baked in or they take the wrapper off the magic box and they have a stack baked in. Yeah? Well, you're hitting on something close. So, finite state machines, DFAs, it's just a big loop. That's tail recursion. Context-free grammar says, I don't know, I'm going to define this string in terms of these 4 recursive strings. But the 4 recursive strings are all independent. So the shape of the recursion that you get is a tree. And so context-free grammars are a way of essentially saying, I can encode this recursive tree structure in a string, and the grammar allows me to extract that recursive tree structure back. But I can't do more interesting structures than that. Whereas on a Turing machine, I can do pretty much anything. So I can do everything that a context-free grammar can do because there I can implement the stack myself and essentially do the depth first search of the recursion tree that you already know how to do when you just do recursive function calls. But I can also do really bizarre things like I don't have a call stack, I have a call tree where depending on the stack frame that I go to when this subroutine finishes isn't the one that called me, but maybe its twin over here in this parallel universe. You get these very bizarre things that one can build in using a Turing machine model, or in fact encode on a computer that seem completely useless and probably are, but it allows you by building up more and more levels of these tapes and so on, you can endow these Turing machines with really complicated abilities. Once you've got function calls, once you've got random access memory, at this point, we've essentially reduced Turing machines to machine language. In fact, even the recursion function calls, machine language implements that as a stack. And at this point, hopefully you can imagine writing a Python program or a Python interpreter in that assembly language, which is assembled down to the machine language, which is simulated by Turing machine. So, Turing machine, at least I wave my hands frantically at this, really does encode what we think computers can do. And there's a name for this statement. The search Turing thesis, which basically says that the word computable means computable by a Turing machine. Now, this is essentially a law of physics. This is not a mathematical theorem because this word here, computable, is not a mathematical abstraction. It doesn't have a formal definition. Whenever anyone tries to put down a formal definition of what it means to be computable, it has turned out to be equivalent to computable by a Turing machine. What you can write to the, When you're writing code in C, you are writing to an abstract machine model. Anything that abstract machine model can do, a Turing machine can do. When you write in Lisp, you are writing to an abstract mathematical model based on Church's Lambda calculus. Anything that the Lambda calculus can do, Turing machine can do. So back to the story about how Turing did this. Church submitted this paper where he invented the Lambda calculus, or discovered the Lambda calculus if you're a Platonist. And Turing submitted his paper on Turing machines to a journal. Journals send out their papers to be refereed. Here is a paper, somebody's claiming to solve the Entscheidungsproblem. Who am I going to send it to referee? The last person who wrote a paper on the Entscheidungsproblem, Alonzo Church. So Turing's paper went to Church to referee. Church responded by saying, have you seen my paper? And by the way, you're a PhD student at Princeton now. Turing said, oh, I haven't. Quickly wrote an appendix to his paper proving that everything that Church did, he did as well. So he showed how to simulate the Lambda calculus using a Turing machine. Turing joined the PhD department at Princeton. Magically, his paper was accepted. And then he went on to do stuff for his PhD. This wasn't even his PhD thesis. This was his admissions essay. Okay? This was his statement of purpose. There was a previous thing, Church's thesis, that says everything the Lambda calculus can do, it can do anything that involves anything computational. That's what the Lambda calculus is. And Kurt Gödel down the street at the Institute for Advanced Study, which is also at Princeton, went, maybe. But when Turing's paper came in, Gödel said, okay, done. This is it. This proves that mathematics cannot be mechanized. This is the death knell for the Russell and Whitehead and Frege and Bourbaki's efforts to axiomatize, formalize all of mathematics in a way that everything could be mechanically checked. It's hopeless. There's no way to do it. Good. I can finally sleep. Most of the people who contributed to that research program ended up in insane asylums. I'm not exaggerating. Cantor, you may have heard of Georg Cantor. So one of the things that fed into this proof by Turing was Cantor's diagonalization argument for the reals not being the same number as the integers, same cardinality. There are multiple types of infinity. Cantor ended up in an insane asylum, partly because he just couldn't wrap his head around the consequences of his theorem, and partly because a significant fraction of the mathematical community said, that's ridiculous. That can't possibly be true. And Cantor couldn't wrap his head around how mathematicians could be so insistent on their belief that there's only one type of infinity when the theorem says otherwise. Right? Before Cantor, Gottlieb Frege was one of the first people who tried to build a systematic development of set theory and logic. I believe he ended up in an insane asylum and killed himself. Turing's story, unfortunately, also has a bad ending. So Turing went on to be one of the central figures in the British intelligence during World War II. He developed a machine at Bletchley Park called the bombe, B-O-M-B-E, which was critical in breaking the Enigma cipher that the Nazis were using to communicate with each other. Really deserved knighthood for his efforts. There are a bunch of other mathematical things that he did, but in terms of actually saving lives, hundreds of thousands of lives, Turing's contribution to the effort in World War II was absolutely phenomenal. Unfortunately, Turing was gay. And being gay in the 1930s in Britain, or 1940s in Britain, was a crime. And because of this crime, Turing was sentenced to chemical castration, and he became depressed, and he committed suicide. The British government finally apologized, but not pardoned, just apologized, in 2015. Alan Turing, he sort of gave us computer science. He saved hundreds of thousands of lives. That's what we should remember him for. But it's often sobering to remember that lives often have other aspects that are not nearly as pretty. Okay, with that, Thursday we'll see you for a review session. We'll talk more about this stuff later in the semester.
When you simulate like memory register, all of those with the Turing machine, or each of them still like can be arbitrarily long?
Yes. Each of those can be arbitrarily long.
Okay. I just find this lecture being very philosophical.
Well, so I can't really go into technical details because, frankly, the technical details are boring.
Okay.
And we're not going to apply the technical details. It's more the power of the Turing machine model is just the model exists.
So that we have some basis.
So you have basis for computing and actually being able to prove in a convincing way. You can't compute everything. You can compute a lot of things. You can compute them with this simple machine.
So what's the relation between building up a formal math system with respect to computing? So, like the big question you mentioned, like everything can be every math system can be constructed like mechanical.
Right. So the question was, if I write down a theorem in number theory, is there an algorithm that can take that theorem and spit out a proof? And a proof is just a sequence of symbols written in some finite alphabet, Unicode UTF-8.
Okay.
That at the end, if you understand the rules of logic that are being applied, convinces you that the theorem is true.
Okay. But how does the halting problem prove it's wrong?
Because I can write a program that says, find a proof for this theorem. And then I can step back and say, does that problem halt? Right, so if I can find a proof for the theorem, return the proof. If I find a proof that the theorem is false, loop forever. Now, the haltingness of this computer program is equivalent to the truth of the theorem.
But why would you assign infinite loop to if it's wrong?
Because I'm trying to prove that there is no proof, right? I'm saying, suppose I could decide whether any given statement in mathematics is true or false using a computer program.
Mm-hmm.
Okay, that computer program is now part of my software library, and I can invoke it however I like.
Right.
So I'm going to invoke it the following way. I'm going to say, my new program says, you give me your theorem. I'll call this oracle that says whether it's true or false. If it's true, I will halt and say, yes, it's true. If it's false, I will loop forever.
Why won't I say
Now, I'm designing the program. I get to decide what my program does. I'm deciding that my program is either going to say yes if it's true or loop forever if it's false.
Okay.
Now, deciding whether my program halts, same as deciding whether that theorem is true. But I can't decide whether my program halts. That's impossible.
But does that?
Which means I can't decide whether the theorem is true. That subroutine doesn't exist. This is a bizarre game that we'll get to later in the semester, where you say, Assume I have a program that does X. If I had a program to do X, then I can also do Y, but I already know Y is impossible.
Oh, it's like the NP thing.
It's exactly like the NP.
Oh, okay.
Yeah.